Hello everyone, welcome to this 16th lecture in the NPTEL course on Riemannian geometry. So last time we introduced this operator dt which takes in a vector field along the curve gamma and spits out another vector field along the curve gamma. So you should think of this dt as the covariant derivative along gamma or the directional derivative with respect to the velocity vector gamma dot of t. Okay. So more explicitly we had the following formula. So if we choose local coordinates, then dt of x is given by this very explicit formula. Okay. So then at the end of the lecture I made the following definition. A vector field x along gamma is called parallel if its derivative with respect to the velocity vector is 0. Okay. So today I want to address in this lecture I want to address the problem of whether one can actually construct these parallel vector fields or not, right. Okay, so here's the main proposition that we want to prove in this lecture. So let gamma be a smooth curve given any time t naught in the interval and any vector v naught in the tangent space to m at gamma of t naught, there exists a unique vector field along the entire curve such that x is parallel, so dt of x is identically 0 and it satisfies the initial condition that x at t naught is precisely this vector v naught. Okay. So the proof of this proposition is going to rely on the following basic existence theorem for linear ODEs, ordinary differential equations, and the key point here is linear. Okay. So let me remind you of what this says. So let A be a continuous function from an interval into the set of n cross n matrices. Okay, so this is the set of n cross n matrices. Okay, then if we let t naught be and suppose this is a continuous function. So let t naught be in I and let v naught be some vector in Rn, then there exists a unique solution to the following system of ODEs. So you take x prime of t, you want it to equal a of t times the vector x of t. Okay, and at the initial time t naught you want x of t to be v naught, and moreover if A is a smooth map, this implies that x is a smooth map. Okay. So I mean this theorem is proved in any first course on ODEs, and essentially this is sort of a vector valued version of the standard integrating factor method of integrating factor, right. So essentially you have to use the exponential of matrices and so on to solve this equation. But the key point is that because it's a linear ODE, there's a unique solution and the solution exists on the entire interval. So later on in the course we are going to talk about geodesics, and geodesics will satisfy a nonlinear equation. So there you'll only have a local existence result. But here, because as we shall see shortly, parallel transport or parallel translation satisfies a linear ODE, you have a solution on the entire interval I. Okay, so that's a crucial sort of difference to keep in mind. Alright, so now we'll apply this basic linear ODE existence result to prove our proposition. So proof of proposition. So there are two steps. First one does this locally, and then we extend it globally using the uniqueness property. So step 1. As I said, this is a local step. Okay, so suppose I take a time, I have this time t0, and suppose this t0 is contained in a subinterval I0. Let's call the subinterval as A0, B0, such that gamma of entire I0 closure is contained in U, where U is some coordinate neighborhood. Okay, with coordinates x1 up to xn. Okay, so the picture is that you have your M, your gamma might be a really long curve, your t0 is this point, you take a little coordinate neighborhood around this, and then I0 is basically, this is going to be gamma of I0 closure. Okay. Alright, so let your vector field x of t in these local in this local chart be given by xi of t del I at gamma of t. I'll now, because I want to use this existence theorem on linear ODEs, I'll use the notation that x vector is basically the column vector given by these components. Okay. So similarly, my vector v0 I can write as v0 I times del I at gamma of t0, right, because this is in the tangent space at gamma of t0. So again I use the notation v0 vector is basically the column vector given by its components. Okay. So then by the formula for dt that I wrote down at the start of this lecture, x being parallel is equivalent to this vector x satisfying the following equation. So for k equals 1 up to n, the components satisfy the following equation: d by dt is minus gamma ijk of gamma of t times gamma dot I of t times xj of t. Okay, and xk at t0 is simply v0 k. So now in order to connect this to my linear existence theorem for linear ODEs, let A of t be defined in the following way. So the jkth component of A of t is simply given by minus gamma ijk of gamma of t times gamma I dot of t. So here of course by Einstein summation convention you are summing over I, right. So then clearly A is a function from the interval to the set of all n cross n matrices, and it's a smooth function. Okay. Moreover, this ODE, this equation of parallel translation is now equivalent to the following system, that dx by dt is simply a of t times x of t, and x at 0 is this vector v naught, right. But then by our linear ODE existence result, there exists a solution for all t. Sorry, this is only on the interval I naught, because gamma restricted to I naught is what is contained inside the coordinate neighborhood. Okay, so for this entire interval, in fact the closure of this interval, you have a solution. Okay, so that solves the local problem, that you at least have a parallel translation defined on this small segment of your curve. Now you extend this globally. So the second step is sort of the more global step. So for this we write I to be a union of these intervals ik, where k could potentially go from potentially from minus infinity to infinity. Okay, we put ik to be the interval ak bk such that I want the following to be true. So this is ak minus 1, this is ak, bk minus 1 and bk. Okay, so I want ak minus 1 to be less than ak, to be less than bk minus 1, to be less than bk. Why? Because this ensures that these two intervals intersect. Okay. So for instance, in this picture, this will be the intersection. All right, and then I put Jm to be the union of Ik from k equals minus m to m. Okay. So now by step 1, there exists a unique, let me call it x naught, right, defined on the interval I naught, such that dt of x naught is 0 and x naught satisfies the original initial value, initial condition. So now by definition, if you look at, so now the main idea is I want to extend x naught to the two neighboring intervals. So to I minus 1 and I plus 1. Okay, so again the picture is something like this. So you have your original I naught interval, then you have the I1 interval here and the I minus 1 interval here. So you would like to extend this to these two intervals, so that now you have extended your vector field to a larger interval, right? And the idea is that if you look at A naught is contained in I minus 1. Similarly, if you look at B naught is contained in I1. and I already know what the value of x naught at a naught and b naught. So the idea is to use those as the new initial conditions and then extend it to these two new intervals, right. So let me write this down. So then by step 1, we obtain unique x minus 1 and x plus 1 on the intervals I minus 1 and I plus 1 respectively, such that x minus 1 of a naught is x naught of a naught and x plus 1 of b naught is x naught of b naught. Okay, so then because of uniqueness of solutions to the linear ODE, this implies that wherever these intervals intersect, so x minus 1 on the intersection of I minus 1 and I naught is the same as x naught intersected on I minus 1 and I naught, and similarly x plus 1 on I plus 1 intersect I naught is the same as x naught on I plus 1 intersect I naught. Okay. So that means if I define x1 to be x minus 1 on I minus 1, to be x naught on I naught, and to be x plus 1 on I plus 1, this implies that x1 is a vector field along gamma defined on the union of these three intervals, which remember I was calling J1, right, such that it's parallel and of course it satisfies the initial condition that we want. Okay. So now you can do this inductively. So inductively we construct this vector field xm on Jm such that if you restrict it to any of these subintervals, that will agree with XL. Okay. But then because the union of all these Jm's is all of I, we get a vector field X defined on all of I, which is parallel and which satisfies the initial condition. Okay. So this completes the proof of our proposition. So one thing to note is that this sort of thing can also be done for piecewise smooth curves. So for instance, curves that might have these sort of corners, okay, and the idea is that you first do the parallel translation here, then you do the parallel translation here, then you do the parallel translation here, and then you do the parallel translation here, right. So you do this sort of sequentially. Okay. So I've used the word parallel translation quite a few times now. So let's formally write down the definition. So let X be a vector field along gamma which is parallel, so such that dt of x is 0 and let us say x of t naught is some v naught. then we say that Vt, which is x of t, is the parallel translation or parallel transport so I'll use both words, parallel translation or transport of the vector V naught to gamma of t. So in other words, we get a map which I'll denote by P gamma T naught to T. So this is a map from the tangent space to M at T naught, at gamma of T naught, to the tangent space of M at gamma of T. Okay, so you take any vector here and parallel translate it to a vector here. Okay, so we call Vt to be this. Okay. So P gamma T naught T is called the parallel translation map or the parallel transport map. Okay, so now let me just make a remark that this allows us to connect tangent spaces at faraway point. Right, so if you are given an x, if you are given a y, of course we know that in a small neighborhood of x, for any points in a neighborhood of x, the tangent spaces are connected, because in fact you can choose a standard basis, right? You can choose a local frame on the entire neighborhood. Similarly, you can choose a local frame in a neighborhood of y. But if x and y are far away, then there is no obvious way to relate tangent vectors at x to tangent vectors at y. But now parallel transport provides you a way, because you connect this by a path and just use the parallel transport map. So of course this depends on gamma, but at least you have a way of connecting the tangent spaces at these 2 points. And in fact how much this depends on gamma is also an important thing to study, but we will not talk about that in this course. I think that will take us too far away from what should be our main focus. Okay, but let me maybe end this lecture by discussing a couple of important properties of the parallel transport map. So the first is really sort of fundamental, in that if you take the parallel transport map, then this is in fact an invertible linear map, with the inverse simply given by parallel translating from T to T naught. Okay. Or another way of thinking about the inverse is that you just traverse gamma in the reverse direction, right, and parallel transport. So why is it a linear? I am not going to write down the proof of this proposition, but it's a good exercise for you to write down a proof by yourself. Just briefly, why is it a linear map? That's because these parallel transport maps were constructed out of solutions to linear ODEs, and these linear ODEs were homogeneous, right. So if you recall, the linear ODE was of the type x prime is some a times x, right. So this is a homogeneous ODE. So clearly if x1 and x2 are two solutions, then any linear combination of x1 and x2 is also a solution to the ODE, right. So that basically gives you the linearity of this parallel transport map. But I'll leave you to write down a rigorous proof by yourself. That's a good exercise. So instead, I want to show you that parallel transport. So of course, if you have a connection, you give rise, I mean that gives rise to this parallel transport map. But now one can also go in the other direction, that the parallel transport actually can actually be used to calculate what the covariant derivative is. So the parallel transport map completely determines the connection. Okay, by the following formula. So let x, y be vector fields on M, and gamma be a curve in M such that gamma of 0 is P and gamma dot of 0 is x, xp. Then we actually have a very sort of familiar looking formula. This looks very similar to the formula of derivative that we study in a first course on calculus. So this is limit as t approaches 0, you parallel transport your vector from t to 0 minus yp divided by t. So in other words, this is simply the derivative at t equals 0 of the parallel transport map. Okay. Right. So how do you prove this? This involves a trick that's very useful when dealing with parallel translations. So this is a useful trick which we'll again use many times in this course. So we pick a basis E1 up to En of the tangent space to M at P, and let EI of T, capital EI of T, be the result of parallel translating the ith basis vector to gamma of T. Okay, so then because the parallel transport map is an invertible linear map, this will also form a basis, because invertible linear maps take basis to basis. So this is a basis for the tangent space at gamma of T. So in fact, this thing is called a local, this is called a this is called a parallel frame for the tangent bundle along gamma. Okay, so you'll see how calculations regarding parallel transport become really simple in such frames. So note by definition that each of EIs is basically a parallel vector field along gamma. So now we simply let y of t be some yi of t times ei of t. Because EIs form a basis, I can always express yi in terms of this basis. But then if you apply the connection, then what is this? This is simply because gamma is because gamma dot of 0 is xp, this is simply the covariant derivative of y along gamma by our refined locality theorem. But then what is this? This is dt of yi times ei by the properties of this dt operator, that is just yi dot times ei or let me write it like this, d by dt of yi times ei plus yi times dt of ei, but dt of ei is 0, right. So, this is just dyi by dt of ei. Okay, so that's in our proposition, that's basically the LHS. We have now calculated, we have a formula for the LHS. Let's calculate a formula for the RHS. So, the RHS is basically d by dt at t equals 0 of the parallel transport map, right. But what is the what is y? So, y is just yi of t times ei. Okay. So, of course, when I say d by dt, I actually mean the covariant derivative along gamma. Alright, so what is this? P is a linear map. So, this is just going to be yi of t times this. Okay, but by definition, this is simply ei, right, because what was this? This was the parallel transport from 0 to t. But we have already observed in the previous proposition that this parallel transport is the inverse of this parallel transport. So, it undoes, it reverses what the first parallel transport does. So, in all, we have that this is dt at t equals 0 of this, right. Sorry, this should be the derivative, sorry. Okay, so this is the derivative at t equals 0 of y1 yi at 0, right. So this is simply the derivative of yi at t equals 0 times ei, but that was precisely, if you go back to our previous slide, if you plug in gamma of 0, this is precisely d by dt at t equals 0 of yi times ei at 0, ei at 0 is little ei. Okay, so that means that RHS is equal to LHS. So that proves the proposition. So basically, you can recover your connection from the parallel transport map. So in that sense, parallel transport is really an equivalent way of looking at connections, and of course it's much more geometric, right. It involves parallelly moving vectors, so it is much more geometric. All right, so maybe that's it for this lecture. In the next lecture, we'll actually talk about. So remember, I still haven't, for a given abstract manifold, I still haven't told you how to construct connections, right. I vaguely said that you can use partitions of unity to construct these connections, but next time we are actually going to introduce the notion of a Riemannian or a Levi-Civita connection, and then show that these are connections that are especially compatible with the Riemannian metric, and then I'll prove a theorem which will say that such connections always exist on all Riemannian manifolds, and in fact they are unique. They are uniquely determined by the Riemannian metric. Okay, so that's the goal of the next lecture, but maybe I'll stop here. Thank you for your attention, and I'll see you in the next lecture.